Hello everyone, we are Diabetes Group 2. My name is Ivan,
My name is Bo. My name is David.
and we're also speaking on behalf of Mette. Diabetes mellitus, or simply diabetes, is a group of metabolic diseases that are characterized by elevated blood glucose levels. It is one of the oldest diseases known to man, as it was first reported in Egyptian manuscripts about 3,000 years ago. Today, diabetes persists, and it has become increasingly apparent that it is a worldwide epidemic with approximately 371 million people afflicted by it. Furthermore, it is estimated that by 2030, 500 million, or that is more than 1/2 billion people, will have the disease. There are different types of diabetes, but type 2 diabetes is by far the most prevalent form, accounting for 90 to 95% of all cases. In order to understand the pathophysiology of diabetes, we must first take a look at the anatomy of the pancreas. The pancreas consists of both exocrine and endocrine compartments. The exocrine portion makes up 98 to 99% of the entire pancreatic tissue and consists of acinar and ductal cells, which are responsible for producing digestive enzymes and bicarbonate that help neutralize the stomach acidity. The endocrine compartment makes up only 1 to 2% of the pancreas and is comprised of small clusters of cells known as islets of Langerhans. These cells include alpha, beta, delta, gamma, and epsilon cells, all of which are important for regulating metabolism. Beta cells are particularly critical in diabetes, as they are the insulin-producing cells of the body needed to decrease glucose levels in the blood. More importantly, they are the cells that are disrupted in diabetes. Due to the large prevalence of type 2 diabetes and because of time constraints, I will focus on the mechanisms of type 2 diabetes. So what causes type 2 diabetes? Even though the exact cause is not fully understood, evidence suggests that genetics plays a strong role in the onset of type 2 diabetes. Twin studies, for example, have found that when one twin has type 2 diabetes, the chances of the other twin developing are more than 70%. Environmental factors such as obesity, lack of physical activity, and even viruses have also been implicated in the onset. In order to have type 2 diabetes, two conditions must be met. First, insulin resistance must be present. Insulin resistance is the state in which the cells or tissues of the body become resistant or insensitive to the insulin produced by the body. In addition, beta cell dysfunction must occur. Beta cell dysfunction can arise via different mechanisms, such as endoplasmic reticulum stress or oxidative stress, caused by the already present hyperglycemia. Inflammatory cytokines produced by infiltrating immune cells can also disrupt beta cell function. It was previously believed that these mechanisms led to beta cell dysfunction, followed by beta cell death. However, a recent and interesting hypothesis has emerged. A recent report published in Cell in 2013 suggests that metabolic stress does not lead to beta cell death, but rather beta cell dedifferentiation or transdifferentiation. Dedifferentiation is the process by which one mature cell type regresses into an immature progenitor stage. More recently, another group found that when the source of stress is removed, such as by providing insulin therapy, beta cells return to their original state. There are different therapeutic strategies for type 2 diabetes. One could, for example, target beta cell function by increasing insulin output. This method, however, could result in increased beta cell stress over time. Another strategy could be to control beta cell mass. This could be done by increasing beta cell proliferation or inhibiting beta cell apoptosis. One drawback is that some patients have a significant reduction of beta cells to begin with. Finally, a novel method that demonstrates great promise is that of transdifferentiation. This could be done by converting exocrine cells to beta cells, other endocrine cells such as alpha cells to beta cells, or a completely different type of cells such as intestinal or gut epithelial cells to beta cells, which is the focus of our presentation. Recently, it was reported that inhibition of a transcription factor known as FOXO1 could lead to the generation of insulin-producing cells in the gut. Diagnosis of diabetes is traditionally based on plasma glucose criteria in the form of either a fasting plasma glucose or an oral glucose tolerance test, where plasma glucose is measured 2 hours after oral intake of glucose. A newer option is the A1C test. A1C reflects average glycemia over several months, and it is shown to have great predictive value for diabetes complications. Aside from being a diagnostic tool, the A1C test is also used to evaluate and optimize the treatment of diabetes, along with patient self-monitoring of blood glucose.
Treatment of type 2 diabetes is centered around reaching a normal or near normal glycemia. This is a dynamic process that is initiated with non-pharmacological part of the dietary modification, exercise, and weight reduction. This is normally combined with monotherapy of metformin. Metformin is an insulin sensitizer and hence targets the insulin resistance. If the patient fails to meet the target A1C of the metformin, current guidelines recommend adding a second oral or injectable agent, such as insulin. Besides insulin, the options are thiazolidinedione, that, like metformin, is an insulin sensitizer, or to add sulfonylurea, DPP4 inhibitors, or GLP-1 receptor agonists, which are all secretagogues, meaning that they increase the insulin output from the pancreas. Sulfonylurea increases the insulin release by inhibiting the K-ATP channels of beta cells in the pancreas. DPP4 inhibitors inhibit glucagon release through increased incretin levels. GLP-1 receptor agonists are injectables that increases insulin release by binding to the GLP receptor. Current treatment of type 1 diabetes primarily consists of treating with insulin. It needs to be injected in the body rather than being taken orally, as the digestive system breaks it. Insulin is obtained from genetically modified bacteria. The amino acid sequence can be changed through genetic engineering to differ its characteristics of absorption, distribution, metabolism, and excretion. The types of insulin available are moderated to act with different speed to achieve an optimal level of blood glucose throughout the day. Regular insulin injections can cause problems, and researchers are working on ways to improve the intake. There are 4 main ideas. Development of skin patches and even implants can allow direct absorption of insulin. Small pumps, even nanopumps, are being developed that can inject insulin in a more controlled way. Inhalers can enable the hormone to be absorbed through nose and mouth through the blood. So far, the method has not been very successful. The pancreas and islet cells can be translated from donors. This can make individuals with type 1 diabetes no longer have the need to inject insulin. A 5th idea is to actually grow beta cells from stem cells, but this is further out in the future. The overall market for type 1 diabetes, as shown in Figure A, has recently been dominated by insulin replacement therapies, which is a life-saving treatment but not a cure. Insulin sales are projected to hold a significant market share in the short term. Other therapeutic approaches, such as using immunomodulators or regenerating beta cells, are still in early development stages. However, their future outlook is highly promising. In terms of recent and projected global market statistics, type 1 diabetes accounted for $8.3 billion out of the total diabetes market of $29.3 billion in 2010. By 2017, type 1 diabetes is expected to account for $13.2 billion. In contrast to type 1 diabetes market, for type 2 diabetes, newer drugs such as DPP4 inhibitors, GLP-1 agonists, and SGLT2 inhibitors are already capturing substantial market shares, as shown in Figure B. SGLT2 inhibitors in particular are anticipated to achieve blockbuster status with their convenient once-daily oral regimens and additional benefits, such as weight loss and lowering blood pressure. Type 2 diabetes accounted for over $21 billion in 2010 and is projected to account for $34 billion by 2017. Since type 2 diabetes comprises approximately 90% to 95% of all diabetes cases, it has arguably the best market potential. Recently, the global diabetes market has been dominated by major companies like Novo Nordisk, Sanofi, Merck, and Eli Lilly. Novo Novo Nordisk is the leader in the insulin market. Out of the top 10 best-selling drugs in 2013, Novo Nordisk produced half of them. They provide a complete insulin portfolio, including Novolog, Levemir, but they also sell anti-diabetic drugs such as Victoza. Sanofi is another company that has gained a lot of success from their blockbuster Lantus, which was the first ever long-acting basal insulin product. They're also known for Lyzumia, which is a once-daily GLP-1 agonist. Merck is also a big company that has achieved market leadership for non-insulin anti-diabetics. Januvia, a once-daily DPP-4 inhibitor pill, was their blockbuster product. Finally, Eli Lilly is known for Humalog, which was the first insulin analog to enter the market in 1996. The figure here from 2012 illustrates the competitive landscape specifically for type 2 diabetes insulin products. The best-selling insulin products from the previous slide, such as Novolog, Humalog, Lantus, and Levemir, are also all shown here. Additionally, this figure shows many pipeline products in various development stages from all sorts of different companies. The landscape for non-insulin products is also highly competitive. Newer anti-diabetic drugs such as DPP-4 inhibitors, GLP-1 agonists, and SGLT2 inhibitors are already dominating the market, and a huge majority of pipeline products fall in these classes. Current top sellers mentioned previously are also seen in this figure. Although the competitive environment is very crowded, the type 2 diabetes market is still expected to undergo substantial growth, and a shift in the landscape may be imminent due to recent research developments.
Hi, I'm David Peprah, and I'll be discussing FOXO1 ablation and inhibition for endogenous insulin supplementation as our proposed therapeutic intervention. Recent studies of FOXO1 ablation in the gut have suggested it may be possible to genetically induce an exogenous source of insulin. FOXO1 is a key transcription factor involved in beta cell identity, and conversely in suppressing the conversion of gut cells into endocrine progenitors. Within the past year, the Achille lab at Columbia University have found that ablation and inhibition of FOXO1 in iPS-derived human organoids is a functional surrogate for insulin secretion. NEROG3 positive gut endocrine cells are converted to insulin secreting cells that are glucose responsive, express most of the beta cell markers, and readily regenerate when FOXO1 is ablated. This suggests there is an opportunity for endogenous insulin supplementation that potentially will obfuscate the need for a chronic insulin injection. We propose a two-pronged approach to modulating FOXO1 activity in the gut as a diabetic therapy. On the right, we have a traditional small molecule approach in which we perform high-throughput screening for small molecules that inhibit FOXO1 activity in the gut. On the left, we have a cutting-edge approach to adapt CRISPR-Cas, which I will go into as a new therapeutic modality to ablate, that is, remove FOXO1 genetically. We will then propose a potential means of delivering the CRISPR-Cas payload. Both approaches will have the same ends: gut endocrine progenitors that produce insulin in a glucose-responsive manner. Genome editing has emerged as a viable therapeutic modality to permanently fix genetic defects and conversely modify the endogenous functions of cells for repurposed capabilities. Clustered regularly interspaced short palindromic repeats, CRISPR is the preeminent platform for precise single nucleotide resolution gene editing for robust knockout or insertion. Using the adaptive immune system of bacteria against phage invasion, Jennifer Doudna and Emmanuel Carpentier were able to elucidate the activity of Cas9, and George Church and Frank Zhang were able to apply it to mammals. Application of this simple system to ablate FOXO1 only requires the delivery of a 20 nucleotide guide RNA that will base pair to FOXO1 encoding DNA, and Cas9, the protein that performs the double-strand break. When delivered, the CRISPR-Cas system should perform a double-strand break, and non-homologous end joining should cause a sequence change in the genome, thereby knocking out FOXO1 expression. We will utilize a recently published cationic lipid system from the Liu lab at Harvard that harnesses the negative charge properties of proteins to interact with positively charged cations. The cationic lipid cargo then fuses with the cell membrane and delivers the CRISPR system intact. The Liu lab have proven this method to be efficient in vivo. Non-invasive GI endoscopy will be performed to deliver the cationic lipid CRISPR payload to guide injection into the gut. GI endoscopy is a generally minimally invasive outpatient procedure that is relatively inexpensive, on the order of hundreds to a few $1,000s. The small molecule approach will focus on inhibiting the phosphorylation of serine residue 256 on FOXO1. Phosphorylation events of serine residue 256 determines the localization and DNA binding affinity of the transcription factor FOXO1. Thus, FOXO1 will be sequestered to the nucleus, is sequestered to the cytoplasm and will have a weakened binding affinity for DNA. Just to reiterate, the potential benefits are production of a lifelong endogenous insulin source that reduces or obfuscates the need for insulin injection in a minimally invasive procedure. There are some limitations to be disclosed. First, targeting FOXO1 expression in a tissue-specific manner, such that FOXO1 activity is not affected elsewhere in the body. Characterization of gut endocrine progenitors, anatomy, and development of biomarkers will be necessary to ensure appropriate delivery. Second, CRISPR has a complicated patent landscape with multiple startups and the Broad Institute pursuing exclusive patent rights. Third, the means of delivery for the small molecule. Essentially, how will it be absorbed? According to the first pass effect, the intestine is one of the primary sites for drug metabolism. Lastly, type 2 diabetes is a systemic issue, with insulin resistance occurring at other tissues. How will this affect type 2 diabetes management? To address these concerns, we propose future experiments to determine the pharmacology of the small molecule metabolism once an appropriate molecule is developed and packaged. Then we will need to perform substantial mouse model studies to determine the side effect profile of both genetic therapy and drugging. Lastly, we will have to optimize the CRISPR-Cas targeting system to minimize off-target effects. Thank you for your time.
This concludes our presentation. If you have any questions, please feel free to comment or email us directly. Thank you.